All right, so let me start by thanking the organizers for giving me this opportunity. As advertised, I'll be talking about cosmological graphs from scattering amplitudes. This is based on the work done over the past 3, 4 years with the following set of wonderful people, and I'll also have some overlap with Evo's talk in the same conference. Excellent. So let me start with some very brief motivation. As all of you know, in flat space, most of the observables we construct are done out of what's called an S matrix. And these objects quantify a scattering process, which is really one of the most basic things we can think of. However, the S matrices that we like to work with are often not the final physical observables. The actual observable that we like working with are things called cross sections. And those are the things which you can actually measure in experiments. And to compute a cross section, you don't end up computing an S matrix directly, but you end up squaring the S matrix and perform some further integrations. For instance, you first compute some in-out correlation function, which is the example of an S matrix with some evolution operator. And then you square this object, which gives you the following structure. And then, depending on the situation, you perform some integrals over the final phase space, or the phase space of the out states. And these objects are examples of what are called in correlation functions, as because you can see that you can sandwich them between two in states. And they, in general, comprise sets of observables. Okay. Now, the typical approach to actually doing this computation in practice is to first compute an S matrix, and then you square and integrate it. And to do that, we use perturbation theory, and we work with what are called Feynman diagrams in momentum space. So the example of a Feynman diagram is of the following kind, where you have some coupling constants of the theory, which is given here, and some propagators. Okay, for example, for this in this particular simple case, it's simply this rational function, which has some dependence on the form momentum and various masses of the theory. Now, working with these Feynman diagrams can get complicated beyond some simple examples, as they involve many things which, are sort of spurious. For instance, in this case, that can involve particles which are off shell, and then you can have poles in the intermediate steps which all cancel out in the final answer, but they still appear in the intermediate step, and hence the name. And in general, they can involve very heavy algebra when it comes to simplifying things. And these kind of computations are difficult even in flat space, with many examples that have been known in the past. For instance, if you try to compute a 4-point function in gravity, which is a computation done by DeWitt, he found that he actually computed the scattering cross-section for this process, and he found that the final answer was much simpler than all the hard work he had to do in the intermediate steps. And he conjectured that there should have been an easier way to do the computation. There was a very similar quote in a paper by Park and Taylor, which is perhaps more well known to people, and they also had a similar observation. This easier way was eventually developed in the early 2000s, and today we have what's called the Amplitudes program. Um, Now, the take-home message from this historical fact is that the final answers can often be much simpler than your building blocks. And to see the simplicity, you may have to make some choices for helicities or the masses and so on, but in the end, it's very likely that your final answer can be super simple. So moving forward, the kind of questions that I'd like to focus in this presentation is how do we think about observables in curve space? Okay, some examples of in correlators. And can we get these observables directly without having to compute this um, analog of the amplitude? Um, for instance, can you compute the scattering cross-section in flat space without having to compute the S matrix? That's the kind of question we'll be asking. But for a set of observables, which are called equal time in correlation functions, and these are simply the most basic thing you can think of, which is simply the insertions of some points at different spatial locations, but at the same time slice. Okay, you just insert some points and you take the expectation value. Now, in the context of inflation, there is a good motivation for studying these things, at least for low enough points. But in general, these are more ubiquitous objects, and things like this also appear in other contexts. For example, these are objects which appear when you're computing Schwinger-Keldysh correlation functions, and that gives you a good opportunity to study them. And even if you're not interested in those things, you might only be interested in studying about these wave functions or the state in which you evaluate these expectation values, and they are often related to ADS correlation functions by analytic continuation. Good. So let me just state the final result. Um, and what I'll try to argue is that these in correlation functions, there's actually a very hidden simplicity that works when you try to sum over various building blocks, and you find that the final answers are much simpler than the building blocks. And in particular, this kind of insight can be realized in terms of an explicit formula that allows you to write these in correlation functions as an integral transform over flat space Feynman diagrams. And I'll explain what this is. And using this, we can find some very non-trivial consistency conditions, understand some loop integrals, and so on, which I'll discuss. Good. So let me state my conventions. I'll mostly work in what's called a de Sitter 4, which has some metric of this kind, although many things I'll say can also be worked out for flat space. And I'll be evaluating these correlation functions at late time, which is near t goes to 0. And I'll work in something called momentum space, which is defined by taking a Fourier transform along the spatial direction and is given by this object. And I'll also loosely use the word energy, which simply stands for this thing, where these are the different spatial components, although there's no notion of conserved energy in this case. Excellent. So the in correlation function, as we saw before, is simply defined by this object, but this is now written in momentum space, and it can be expressed as a very familiar formula in quantum mechanics, as some some field insertions with some probability distribution given by mod psi square. Okay, so as long as we know what the expression for the wave function is, we can compute this path integral and get the answer for the correlation function. Now, the state that we are going to work with is what's called the Hartle-Hawking or the Bunch-Davies vacuum, and it can be constructed out of a path integral of this kind, where you have some initial condition defined at early times, which for our purpose will be simply set to 0. This simply means you're starting with a free field at early times. It's basically a Gaussian state, and then you let it evolve, and the field gets some profile at late times, and the overlap of that profile with your field with the state is given by this path integral. And this is exactly the same path integral you would do if you're computing ADS correlation functions. Okay. Now, if this was unfamiliar, this is also the statement that this wave function satisfies the Schrodinger equation, at least without gravity, and even with gravity, there's a very similar equation you can write down, but it's simply the Schrodinger equation. Now, just like we have Feynman diagrams that allow us to compute amplitudes or the S matrices in perturbation theory, you can also compute these wave functions diagrammatically using what are called Witten diagrams. So just to give you an example of how this looks like in perturbation theory, this is the object that we want to work with, and you can expand this perturbatively in some field basis, which is given by these phi's here. They're very similar to the position the position space representation of some wave function in quantum mechanics. And the coefficients of these fields here are what are called wave function coefficients, and these are the data that we're interested in computing. And these are also the ones which, by analytical continuation, are related to correlation functions in EDS. So just to give you an example, if you're working with some free field theory, then the ground state wave function is simply a Gaussian, where this is the only meaningful contribution, only meaningful coefficient that survives, which is given by the energy of your field. Excellent. Now, as I said, you can organize perturbation theory using some diagrammatic rules. And these are very similar to the standard Feynman diagrams you use, except that you make one time slice special because you're evaluating the wave function on that time slice. So in this case, you can have propagators of two kinds, ones which end on the time slice, which are represented as this, and ones which can, which survive between any two different times. So these are called bulk to boundary propagators because they have one point in the bulk, which is any time between minus infinity and zero, and another point which is at the boundary, which is at t equal to zero. And the more familiar propagators are the ones which can move between any times, and that's the bulk to bulk propagators. So using this, you can construct these wave functions. For instance, you can construct psi4. If you want to do psi4, then this subscript 4 refers to the 4 insertions that you're making on the boundary, okay, which is the 4-point function essentially on the boundary slice. And this phi 4, the superscript here, denotes the bulk in this bulk interaction that happens here. Similarly for phi cube theory and so on. Now, whenever you draw a diagram like this, you should know that momentum conservation only happens along the spatial direction, which is along the horizontal direction, and not something along the vertical direction. Excellent. So just to illustrate how this looks like, let us consider a conformally coupled scalars, which is a scalar field with a very specific mass in de Sitter, although many things that I'm saying can also be generalized for massless scalars. And the propagators for this conformally coupled scalar looks as follows. The bulk-to-boundary propagators are simply plane waves, which look like this. And the bulk-to-bulk propagator are almost the standard Feynman propagators, i.e. the time-ordered propagator, except that they have this additional term that is dictated by the boundary condition that you work with. So for instance, if you work with these propagators and compute a 6-point wave function coefficient in phi-4 theory, you would have to do these time integrals, where these time integrals come because of these two insertions here. And you perform these time integrals from minus infinity to zero, and you plug the expression for the propagators, and you find a very simple answer, which is a rational function in this case. In general, the answers need not look so simple. And this is the example of a wave function. And once we have these wave functions, we can now compute the correlation function. So in one of the previous slides, I showed you how the correlation function can be expressed as a path integral over the wave function coefficients. So we have some wave function coefficients like this. And then in order to get a 6-point correlation function, we have to expand this exponential here. And then we can receive contributions from the 6-point wave function coefficient, which we saw in the previous slide, and also from lower point wave function coefficients like this. So this is an example at the lowest order in perturbation theory. Now at higher points in loops, you can get expressions which are much more complicated. So this is a similar expression or an expansion at the third order in perturbation theory, where you can have many more contributions. Now, what I'll claim now is that the sum, this final sum that you can do is actually much simpler than the initial expectation, and in particular is going to be much simpler than any of these individual terms. So to see that, we actually go into some version of momentum space or Fourier space, where we take the expression that we saw in the previous slide, where we had some product of bulk to boundary propagators and some bulk to bulk propagator. And we express the bulk-to-bulk propagator as an integral, which is almost the same as a Fourier transform, except that instead of exponentials, we have some sine functions, which basically tell us about this boundary condition here. And by doing this, we can now interchange the order of integrals. So let us say I first perform the t integrals, the time integrals, and then I would get something that looks like this. I have some remaining b integral with some rational functions which came by performing the time integral over something that looks like the standard propagator in flat space. Okay, so it looks like an energy integral over the flat space amplitude. However, this doesn't quite work in the same way for higher points in loops. But to our surprise, when we tried doing this for the NN correlator, where we also add the contribution from some lower point function, we found a very similar expression, except that this prefactor was slightly different. And it was very surprising when we saw that the same factor actually works for arbitrary points in loops. For instance, at one loop, you have some expression like this, where you take the bubble diagram in flat space for the flat space amplitude, and you simply multiply with a very similar kernel. And in general, this kernel is theory dependent, and so on. There's also some relation with celestial amplitudes, which I'm not going into right now. But anyway, so this actually led us to a general rule, which we call the dressing rules. And the idea is the following. You take your flat space Feynman diagram, and you simply multiply with the kernel, and you integrate with the energies. And these kernels, we'll refer to them as auxiliary propagators. So you can write them diagrammatically as follows. You take some flat space bubble graph like here, and you multiply with some rational functions like this, and that gives you your cosmological correlator. You could repeat this with a triangle and any other example. So let's see how this is useful in practice. For instance, if you look at the one loop contribution, which was, this guy, if you were to compute it from the wave function point of view, you would have had to sum over these following building blocks here, like this wave function coefficient, and then so on and so forth. And if you actually perform the loop integrals, you would find that all of these things are actually dialogues. Okay, they have some divergent pieces, and along with them, you get some dilogarithms. However, once you add the three terms, and instead write this integral representation, you simply get an infinite integral with some rational functions and a logarithm, which in turn gives you a logarithm again. Now, this expression I'm sure has been discussed in Ivo's talk again, so I'm not repeating it. But this actually shows how the transcendentality drops when you try to go from the wave function to the Indian correlation function. And it's a more general feature that we have now observed for the bubble, the triangle, the necklace, and all the examples we have been able to compute. Good. Now, there's another good application of this whole thing. Um, so, as we discussed, these correlation functions are essentially some flat space Feynman diagrams of this kind with some extra one-dimensional propagators that we had put. Okay, so in this particular example, it takes the following form. Now, you could ask what happens if you take these graphs and you set propagators on shell. Okay. Now, these things have a rich history, like you can relate these to Katkowski rules, and then you can compute sequential discontinuities and ask questions about bootstrap, etc. And for that, you can now you now realize that you have two options. You can either cut these extra propagators, or you can cut your standard Feynman propagators. Now, the cuts of standard Feynman propagators are very simple to what you usually do for amplitudes. However, the cut for these auxiliary propagators are slightly different, and they are closer to what are called mass cuts in the amplitude literature. So just to give you an example, you can take this following graph, and let us say you cut both these auxiliary propagators here, which simply means I'm setting them on shell. So I replace these propagators with some delta functions, and I have one p integral and two delta functions. So essentially it leaves me with one delta function times the flat space amplitude. And this delta function is essentially restoring energy conservation, and hence this is a way to take the flat space limit. Now, how do you implement these cuts? One way to do it is by discontinuities. So the discontinuity of some function of x squared with respect to x squared is simply defined as the following. You simply take the value of the function before and so just above and below a branch cut, and that's defined like this. And for the example of 1 over x squared, doing this simply gives you the delta function. And for any function that depends on x squared by f of square root of x squared, this discontinuity essentially returns the sign flip, okay, which is the discontinuity across the square root branch cut. Now you can repeat this for functions of multivariables, and if you do this for functions of two variables, you simply get an expression with two different sign flips and this linear combination. Now, by relating this discontinuity to the cut, you get some interesting constraints. Because what we saw in the previous slide is that taking a double discontinuity essentially gives you a delta function, which simply means that away from the point k12 equal to k34, this thing simply vanishes. And from the expression in the previous slide, we saw this being related to a sum of four sign flips, and hence we get some expression which tells you that this linear combination must be zero. And this can be extended to any arbitrary points in loops, which is pretty cool. And these I think are also very general, which I'm not going to discuss now. But what is super nice is these are new consistency conditions for the in correlator and not satisfied by wave function coefficients, and hence it tells us something new. Good, so now I'll conclude. I hopefully have convinced you in the last 20 minutes that there's some simplicity of the correlation functions as compared to wave functions. And there are very nice integral representations which hold for in correlation functions in terms of flat space Feynman graphs, at least for some theories. And this actually has allowed us to see some new relations between amplitudes and cosmological correlators. And using these integral representations, we can understand loop integrals and also find some new connections and so on and so forth. So thank you for your attention.